Yeah, so before we start, yeah, we for this presentation, well, discussion, we cherry picked some features, some that are present in newer Linux versions. Even if we are not involved directly in the kernel, our team works with the containers tools. We interface directly with this interface, so we want to share our experience with this and in some cases how we plan on using them, since there are some features that are present in the Linux kernel but are not used by containers tools. Yeah, so please join the discussion and share your experience and let's have a discussion about this. The first one we picked is cgroup v2. We spent a lot of time in the last years to enable cgroup v2. As Dan was mentioning before, we switched the Fedora 31 to use cgroup v2 by default. And we were expecting a lot of troubles at the time, but things went quite well, and we are quite satisfied with what cgroup v2 is enabling. It addresses a lot of issues that were present in cgroup v1. Also, from the containers tools point of view, it's easier to manage, and it's also safer. My favorite feature is that it's possible to safely delegate an entire C group and possibly sub C groups to an unprivileged process or container, and that it's safe to use there differently than C group v1. That it was possible to delegate to other unprivileged users, but it's not a safe operation, basically giving full control on the host.
So cgroup v2 gives us two huge opportunities. One, as Giuseppe was talking about, is you could actually have a container now that could subdivide its C groups. So you might say that a container can only use this much CPU or this much memory, and now inside of the container you could have something like even have systemd running inside the container or some other tools to further subdivide. So individual processes inside the container can have further subdivided of C groups. Also, with something like Podman running rootless, with v1 we had to turn off C groups control in the home directory because there's no way to delegate from the non-privileged access to cgroups v1 because there was no delegation. And with cgroups v2, we can actually have containers running rootless and have them able to manage their own C groups because they could subdivide the users portion of the C groups to the environment. So those are the two major features of that we take advantage with containers. But I think far more important is that the kernel, going forward, the kernel engineers only want to support cgroups v2, and we have to get containers off of cgroups v1 or get the lock. And I think you'll see Kubernetes. Actually, Kerr has been leading the effort to get Kubernetes onto cgroups v2. So, Kerr, you want to talk a little bit about that?
Yeah, I'm mostly on the low level side of things, like runc. But yeah, basically the migration from v1 to v2 has to be done once because it's like the kernel boot parameter, and you cannot like have some containers on v1 and others on v2, and that's a big issue because everyone's keep running on v1, and moving to v2 is like something that you have to like do it, have to decide and do it. And I would say that half a year ago, the situation with cgroup v2 support from runc side was very bad, but it has changed a lot. And since runc released candidate 93, we now fully support cgroup v2, and So in case you run in the latest Fedoras, you can just use it as is. You don't have to change anything. In case you run in any other distro, you have to supply this boot parameter, which is described in the documentation. And from the perspective of the developer, it also solves lots of issues. So can we please have the next slide? So basically, the way cgroup v1 looks like, it's a forest. It's a set of mounts. They are all mounted under their appropriate controllers. So each cgroup controller is their own mount, and there is no standard hierarchy. So the way that it is presented on this picture, it is a standard hierarchy, but it's not set. You can mount it anywhere, and you can have more than one mount per controller. So, and I've seen distros that use some custom paths for these mounts. So every time you work with these cgroups, you have to first figure out where the mounts are and which controllers are mounted to which path. So that's just one of the problems. And the other problems with cgroup v1 is some of the controllers, they not really work. So I have three examples here. First example is kernel memory controller. It allows you to account for and limit the kernel memory used on behalf of the user space processes. And there are two problems with this. First of all, users don't really understand what it means, what's the kernel memory, because user space memory is pretty simple and straightforward concept. Your application takes some memory. And the kernel memory is some that is more complicated. Like you open a file and then kernel allocates some data inside it to hold this file descriptor open, and then it allocates some memory to hold this cache, the page cache, to hold the file contents, and so on and so forth. And all this is a kernel memory. It's not pretty clear how to like what amount of kernel memory would you need for your application. It's very complicated question to answer. So you cannot say like, oh, I need 10 megabytes of kernel memory for this container. You don't know. So, and yet this knob, this limit is exposed. The other issue is the kernel memory is, some of that is not really reclaimable. And once the kernel memory limit is hit, the kernel cannot do anything but deny allocation. And in some cases, actually, it cannot even deny allocation because there are some allocations that cannot be denied within the kernel. So it has to go over the limit. So basically, this thing is not working. And some older kernels, they really, sometimes they even oops in various situations just regarding.
So there was a question. There was a question in the chat about whether or not, once this gets into Kubernetes, can we run sort of a mixed cluster where it have some machines are still at V1 while others are at V2. This is not really a Kubernetes conference, but I believe that will be possible, right? So
yeah,
right now,
I believe so.
Right now, Kubernetes doesn't support cgroup v2. We're hoping by later in the year it will.
Yeah, at the moment, yes, but we are planning like to extend Kubernetes with cgroup v2 only features. Like so when that so while in the long term it won't be possible anymore unless you stick with just what is in cgroup v1.
Right. Yeah. Eventually, the first versions are going to be using cgroup v1 concepts. and then translating them into cgroups v2. Eventually, we hope to get Kubernetes to fully support all of the features that are cgroups v2, at which point you won't be able to go back. But I think there will be a transition time where you might have mixed nodes running. But I think we got to move off of cgroups v2 to
Yes,
because we have a lot more than just this, and we've already used up a quarter of our time or a third of our time. So next slide.
First up, Sandeep, did you have a question, or did anyone else in the panel want to hop in and ask or say anything? If not, yeah. All right, then I will. Feel free to chime in if you want to say anything, or say something in the chat, and we'll poke the panel.
Yeah, there was a question also in the panel about whether or not we'll have cgroups v2 support for Kubernetes in RHEL 8. So the plan right now is just, I would figure it would be RHEL 8.5 or later, depending on how quickly we can get everything working in cgroups v2.
So Dan mentioned some things about the cgroup v2, and the biggest, one of the good features of cgroup v2 is soft memory limits. This is something that is not available in cgroup v1. So in cgroup v1, we have a memory allocation guarantee for the container and the hard memory limit. And with cgroup v2, in addition to that, we have soft memory guarantee and soft memory limit. That's a so-called memory.high and memory.low in cgroup v2 lingo. And those are the soft limits, which are much better than the hard limits, because you can go over the soft limit. And it's not like once the limit is hit, you cannot do anything. What the memory high limit does in the kernel, for example, if you go over the memory high limit, your container, your cgroup, your container will be penalized by slowing it down and doing lots of reclaim. So the kernel will try to reclaim some of the memory, like shrink the caches or whatever. And it will also penalize you by you running slowly. This is basically tries to emulate the same thing as on the real hardware. Then you ran out of RAM and you're swapping out, and you feel your system is slow, but it's still working. It's just becoming slower. So it's very similar concept here. Once you go over the memory high, your system, your container will run slowly, but it will still run. Versus with cgroup v2, it will probably resort to out-of-memory killer, just killing some parts of your container, which is fatal, right?
Yes. All right, let's go next slide.
Before we jump to mounts, there was a question in the chat. I just want to see. Oh no, that's just a comment. Never mind. Sorry. Continue.
Okay, so this is more about the lack of the kernel feature rather than the kernel feature. So there's still one problems I came with than working with runc is getting mounts information. So sometimes you want to get the information about a particular mount point, and the only way to do that at the moment is to get the information about all of them by reading the proc self mountinfo and parsing it and figuring out the various flags. So it's a particularly bad API, and I can say say the same thing about the whole /proc. The problem is it's text-based, column-based, and it's not extensible, and you have to do the binary to text, text to binary translation. And the particular problem with mountinfo is there can be tens of thousands of them, and in order to get information about one of them, you have to read them all. And the kernel provides information about those mounts. It holds various logs inside, and you cannot say you cannot mount at the same time as you're reading mountinfo, as the kernel serves the next page of proc self mountinfo. So it's slow, and it used to be racy. So for example, you read the mountinfos, and there are not all the mounts coming in this file because there was a race in the kernel which was fixed. So sometimes you have to read it twice. And if you want changes, like you can actually poll the mountinfo, so the event will come if the mounts will change, and this is what systemd is using to keep tracks of what mounts are in the system. And then the poll event is delivered. Systemd has to reread the whole mountinfo again and parse it again just to figure out what the changes were. So instead of it's like this mount has appeared or this mount has disappeared, systemd has to read it all and compare. And that makes it slow if there are lots of mounts and unmounts going on the system. That there are bugs about it. And at this point, there is no solution from the kernel. There's just 3 possible solutions. One is fsinfo series by David Howells. And I'm not sure what the current status is, but looks like it hasn't been updated since like April last year or so. The other possible solution is so-called test diag proposed by Andrew Wagen, and it's also not merged, and I'm not quite sure what the current status is. Basically, this is the this is a binary interface that is proposed to replace /proc, in which you can like ask which kind of info you want, and you get back the binary packet with all that info. And finally, there is an idea to try to use eBPF to retrieve some information about some mounts. Currently, this is just an idea. So that's lack of the kernel feature I wanted to mention.
He wants to put pressure on the kernel guys to develop this, but next slide.
Yeah, this is a new feature that went in the Linux 5.10. What we were seeing is that there are certain class of containers, like build containers, that where we don't care about the persistence of the storage. Like I don't know how many times you tried with YAM or APT. Like they tend to ensure that every file installed it's synced to the underlying storage. So they call fsync on each file, and that's a very slow operation, which makes sense when you run them on the host because you don't want files to be half written, or if the node crash in the middle of update, you will not find them on the next reboot. But when we build containers, or when we run containers in production, if something goes wrong, the container it's just it's thrown away, and all the process restarts. So this is a feature that went in the overlay file system that we want to take advantage of in our tools for some kind of containers, so that should make them faster in the end, because they will reduce number of I/O operations. And we are taking advantage of this. That we know that if things goes wrong with the container, it's lost anyway.
Yeah, if you think about say building a container. So when I'm building a container image, you have the build going on and all the steps that are going on inside of the build. If the kernel crashes during the build, you're not really worried about whether or not the files got down or not. When the system comes back up, you're really going to have to rerun that step phase again. So by allowing us to mount the storage basically as volatile, we say that if the kernel crashes during this phase, we're just going to throw it away. When builds complete, what they do is they take the in-memory content and the stuff on disk and actually save it. So this is just for the layer mount or the overlay mount that's in it. Similarly, in Kubernetes world, when you're running a Kubernetes cluster, the container, basically the image that is mounted via overlay is mounted volatile, because when Kubernetes, if the system crashes, Kubernetes comes back, destroys all the containers and recreates them. So there's no reason to pay the overhead of guaranteeing that these syncs are happening. So the volatile is really about speeding up separate kind of workloads. You might also want to do this with, say, a container that you run with a -rm flag. So say podman -rm, we might want to mount that volatile, because you're basically saying you don't care about the container when the container is done, the container image when it's done.
Yeah. Also, I want to add, before we were trying to emulate this file system feature using seccomp, but the disadvantage of that approach is that it was blocking every sync coming from the container. So also, if you have a container with a volume installed, it will block also the sync going to the volume. Instead, what we want to achieve with overlay is that we want to block only the syscalls that they go to the overlay upper dir. Yeah. Also, it's while the sync calls are blocked, you can if you run a container with this option set, and then after, when the container is stopped, you call a sync on the entire file system. Then that's also another use case we are looking at, that the container can, well, it's saved to the storage in that case. And so we avoided the cost at runtime, but once it's stopped, it can be synced just once. Yeah.
All right, let's go to the next slide.
Yeah, this is another cool feature that it's in the kernel, but still it's not supported by OCI runtime specs. Basically, it's possible to emulate some syscalls, like to delegate a user-space program the handling of syscalls. And this requires an agent that it's running for the entire lifetime of the container. And the OCI runtime, like runc run, they just created a container, then they disappear. So the goal here is there is an open pull request for adding support for this, to pass the control to a different process that then will handle the seccomp notifications. Yeah, we still lack support in the containers tools. I don't think there will be a unified way of supporting it. Like Podman, for example, uses Conman for the container shim, and probably the seccomp notifications will be handled there. Or it will be different for Docker container D. Yeah.
Giuseppe, the way this is planned to be used is we could potentially allow containers, sort of fake out a container process that needs to have certain privileges that we don't want to give to the container, but have a separate program that is answering the container. Yes, for like, we allowed you to write to the auditing system or something like that, right? Is that the basic idea? And then we don't have to give you a cap audit, right?
Yeah. There are different use cases. One we were looking at was to emulate cap audit write for unprivileged containers. We just emulate the syscall, the socket syscall that creates the audit log, and then instead of writing to the system audit, we would write these notifications to a per container log file. And another use case could be, for example, to emulate mknode for unprivileged users. Like if you run in a user namespace, you are not allowed to use mk nodes. One way of circumventing this limitation would be to use second notifications that intercept the mk node request and then create the device in the container. Like an unprivileged user could bind mount it from the host if the device is already there. Yeah, but then you can you can emulate in the way you prefer.
All right, next, let's go to the next one.
There was a quick question about volatile being available in.
Yeah, volatile is just getting into Linux kernels now. I think is it in 5.10?
Yeah.
So the 5.10 kernel, I just showed up in Fedora 33. We haven't put it into Podman 3.0. It'll probably be in Podman 3.1 or later. pidfd. Kirk, can you talk about this one? Do you know what?
Yeah, so basically the problem with PIDs is they are recyclable once you run over the PID number, you start from 2 again and so on. And the problem with that is if you have a PID number and then you want to do something with it, like you want to kill it, sometimes you kill the different process than the one that was originally referred to. So the pidfd is trying to solve this problem exactly by providing you a file descriptor that refers to the process, and it will definitely be referring to this particular process, so there's no problem of PID recycling with that. And if you want to check, if you don't have pidfd and you want to check that this is the process I was referring to, you need to read it start time, for example, and then compare it, and then reread the start time again, and then compare it. But this is complex and racy, and many people just don't do it. Even if you do it, there might be a race sometimes. So what pidfd allows, if you do the clone and you put this clone new PID flag into the arguments, then you have the pidfd returned, and then you can refer to it later. And in addition to that, various kernels starting from 5.1 to 5.6, they added a few other ways to work with pidfd. For example, the pidfd open lets you get the pidfd from the PID. And then wait ID, if you set the ID type to pidfd, it lets you wait for this PID. And there's a similar syscall to send the signal. And finally, there is an interesting function that allows you to have the file descriptor of a different process shared with you, like you do dub, but without, not in the context of that other process. I think Giuseppe wanted to say something about that as well.
With pidfd we have the same problem in the OCI runtimes, like secondfd, as we need to pass around a file descriptor. So this is also not supported at the moment by the what the OCI runtime specs and by the and the OCI runtime works. That this requires an agent to keep track of this fd. Well, unless using the pidfd open syscall. But yeah.
Yes. Is there any proposal in the OCI runtime about the pidfd? Because I haven't seen any.
It's part of the second pull request. There is a discussion going on there how to pass fd to the upper layers. The discussion is still going on. But yeah, we didn't come to an agreement on this.
Okay, next slide.
I can talk about it. So basically, you want to close the extra file descriptors that you happen to have before doing exec, for example, for security reasons. So that you won't share the unwanted extra file descriptors with your child. And the way you would do that, and it's actually a pretty good way in the upper box, is you iterate over what you find in proc self-fd and either do close or set the exec flag on this file descriptor. And this is slow and racy. And there is a worse way than that. So if you don't do that, the other way you would do that is you query the system, like what's the upper limit on the open file descriptors, and then you just call close on every one of them. And there was a bug in RPM plus Docker, pretty interesting one. The people complained that RPM installations are much slower inside Docker than on the host system. And it happened to be that the Docker sets the very high U limit for number of open files, like 1 million or so. And the Docker and every script it run, like the RPM post install script, it happened to call close 1 million times. And it did so, like, you can imagine if you install 100 packages, each of them has pre-installed post-install scripts, everyone calls 1 million closed syscalls. That's a nightmare, and it could be like, it was like minutes slower than on the host. So the close range is a syscall that appeared in 5.9, and it solved this task by giving the range of file descriptors to either close or set a exec flag. And the other thing that it does is, if you have a multi-threaded program and one thread is closing these file descriptors and the other thread might open some new ones while you're closing them, it can create a race, like you will have some descriptors not closed. So there is a close range unshare flag that what it does, it unshares all the FDs, so this thread will have their own private set of FDs, and then it closes them all. It's basically, it all stems from the fact, but by default, the exec flag is not set on the new file descriptors, and some runtimes solve this problem differently. For example, Golang, in Golang, unless you use like low-level file opening primitives, all the file descriptors are claw exec by default. And then you do exec, you have to explicitly say, like, I want to share this, and this file descriptors, and it will dump them for you. But we cannot, the kernel cannot just change the default from no claw exec to claw exec.
Yeah.
So in all the other systems, they have to use something like this, and close range is a big help.
Yeah. It was actually designed into GCC. So if you go back, you can blame Carnegie and Ritchie for it. So if you open a file inside of any open call inside of C, if you do a fork and an exec, the process underneath you gets access to the open file descriptor. And of course, that made sense for 0, 1, and 2. It probably doesn't make sense for anything greater than that. And but that's the standard going back. With SE Linux, it used to block all leaked, we used to call them leaked file descriptors, and it was probably the #1 cause of SE Linux AVCs in the world was processes leaking. We actually, many years ago, found that the init system was leaking out the syscall to basically reboot the system to every process that it forked. So every process on a Linux system would have access to that socket. So this has always been a big problem, and lots of hacks have been used to close it. So it's nice to see this finally happen. Alvin, you got a question or a comment?
I was just mentioning on the chat about the second notify pull request with the links. That's it.
Okay, good. All right, let's go to the next slide. I don't know how much time we have left. Yeah.
So there's a new sys called openadd2. It's available since 5.6, and what it does, it limits the way that kernel is going out looking for files to open. The problem, and this is a big problem, especially with containers, if there are all sorts of attacks on like trying to escape the container root, or by using like specially crafted symlinks or hard links or whatever, or -- and all sorts of that things. And it was previously attacked by doing lots of checks in the user space. Like there's a, for runc and Golang, there's a package called secure join that lets you like join the directory and the file or prefix and the path within the prefix, and it made sure that the path is not escaping this prefix. And but that was racy and complicated, and you have to stat all the components of the path and so on. So finally it got solved within the kernel, and it's basically the same as open, but it gives you a number of flags that are listed on the slides, and I won't read them all for you. Now OCI runtimes can use all these things to make sure whatever we open for on behalf of this container or for this container are not escaping. Currently, runc uses this for cgroup files to make sure that whatever cgroup files we open, they are all belongs to sysfs cgroup. And then I talked about mountinfo above. One thing that you need to consult mountinfo is if you want to check if the given path, if the given file or directory is a mount point. This is impossible to do without mountinfo in case this is a bind mount, because usually you just compare the stat of do the couple of stat syscalls and compare the device and inode number of this entry and its parent, but it's not working for the not always working for the bind mount. So this little package mountinfo is using openadd2 to figure out whether a given path is a mount point.
So if you look, if you, I mean, the classic attack vector here is, well, Docker copy and Podman copy are the two places where we have to be very careful with this, because what usually you're doing is just say copying something from the host into a container image. Well, if the container image has a, say, you know, an attacker basically puts something into the container image that has a symbolic link attack on the host, they might be able to trick you to copy a file in that you think is going inside the container and ends up going, you know, out to the host, you know, maybe overwriting etc shadow or etc password and things like that. So these are the types of attacks. And with openadd, we can basically say, I'm going to open this file, and that file cannot point outside of this path. So you can put in the path of the volume of the mount of the image. And now if I copy on top of a file that is a symbolic link attack, basically is this, you know, it's a file that's pointing out, you know, through .. / blah, blah, blah. The kernel will stop it and prevent it. Whereas we had to do all that in user space, and in user space, we're often buggy. So the kernel has a lot more of that information. So that's real benefit of this. Caesar, you got something to say?
Yes. Hi, everyone. My name is Cesar, and I am one of the developers on sort of a custom runc runtime called Sysbox that tries to enable containers to run, rootless containers to run things like Docker, systemd. And I wanted to mention that we are using currently the second notify mechanism to emulate portions of procfs and sysfs, and to intercept, particularly intercept certain syscalls like the mount system call and so on. And one of the questions that I had was, as far as kernel features, one of the things that I think will be really cool in containers is for procfs and sysfs to be further namespaced, because that's some of the trickery that we're playing, is that it's not fully namespaced. There's plenty of holes there. And so when you're running microservices, okay, but as soon as you start running more complex programs, procfs and sysfs more deeply, things break. There's a lot of host information being exposed through hostfs, through procfs and sysfs into the container. Any plans on working in that area, sort of further namespace procfs, sysfs, and hide more things inside of it, hide more host information from inside the container?
Yeah, that's actually a big problem that is still not solved, and I haven't seen any advances in the kernel recently, and you're probably aware about LXCFS that solves this through the fuse, and yeah, I can only hope that kernel guys will eventually get to it.
Yeah.
I know
there's been some. Yeah, there's been some efforts to have a new type of proc file system, and that's been worked. The problem is, I've been dealing with this back to before Docker was created. Right, this goes back 8-9 years, and sometimes things in the kernel work at that speed. So it's yes, there is an effort. There are people looking at this, but it seems to move at glacially slow speeds. So. It's usually, like the open ad is container people going in and working on the kernel as opposed to relying on kernel, traditional kernel people doing it. So I think so yes, everybody knows about it, but it just hasn't happened yet. So
yeah. So we ended up doing something similar to what Giuseppe was mentioning, emulating procfs and sysfs in user space, with the daemon, and then using the second notify to intercept the mount system call. So any mounts that are occurring inside of the container end up mounting the emulated procfs, sysfs, as opposed to that. Thank you so much.
Yep. Let's go to the next slide. Giuseppe, take this.
I take it? Okay. Yeah, this is another cool feature that went in 5.11 and that finally enables rootless containers to use overlay in the same way as rootful containers. Before, overlay was not allowed in a user namespace, so we were limited for rootless containers to use a fuse file system for emulating their overlay storage model. But since 5.11, it's possible if the user in the user namespace as capsysadmin can mount an overlay file system, and so that. This was a big limitation for rootless because fuse is significantly slower than native overlay. It's very similar to our rootful overlay works. The only difference is that it uses a user extended attribute to store the overlay metadata instead of the trusted. There are some also limitations in the features that can be used, like I think cannot be enabled because otherwise an unprivileged user could forge a file that's allowed to read files it as an access to on the host. Yeah.
So first of all, I want to point out, so the way we work with rootless containers is we're using user namespace, and in the kernel, if you're in a user namespace and you're in your own mount namespace, then the kernel basically allows a non-privileged user to do certain types of mounts. These are procfs, sysfs, tempfs, I think devpts, fuse file systems, and bind mounts. Those are the only ones that have been allowed up to this point. And I'm going to toot Giuseppe's horn here because he saw the problem of not being able to use overlay. So traditionally in Podman, the first time was just VFS, and VFS is really a horribly slow file system and really uses up a ton of file system driver and uses up a ton of disk space. And so Giuseppe built a thing called Fuse Overlay. He took what was implemented into the kernel for overlay and rewrote it in a Fuse file system driver. And that's been the way we've been doing overlay file systems for rootless overlay file systems for the last 4 years. And it's been great. It really works wonderfully. The problem with it is it's running in user space. So if you, so sometimes people compare root, say Docker running as root to Podman running rootless, and they say, well, Docker runs much faster, and really what they're comparing is apples and oranges, because Docker is using host overlay file system where Podman is using Fuse overlay. So when I go, say if I'm doing something that's really hammering the file system inside of the container image, like a large install, like a build, where I'm writing tons and tons of data to the file system, that's happening in rootless mode, goes into a user space process. That process then is taking that data and handling and then writing it to real file system. So when we swap out, if we can, as a rootless user, swap out from Fuse file system to overlay, we eliminate that overhead. So we should be able to get the same type of performance for writing large images as we do in root full mode now that overlay is. From the kernel point of view, what they were worried about is, they basically have to go every time they go through a file system they want to allow for rootless, they have to investigate how a hacker could attack the system, and overlay file systems basically write these special devices to basically take care of things like deleting files, adding files, and those required privilege. So they really had to investigate allowing that. So now we'll have, as of 5.11, which I don't think is released yet, we will have the ability to do rootless. So we're starting to work through the container engines to support rootless mounts, if rootless overlay mounts, if they're supported, and we'll see that going forward probably, sometime later this year when that kernel becomes more prevalent. Also, we will continue to use Fuse Overlay because Fuse Overlay has some really nice features that we'll be talking about probably later on in this session. But Fuse Overlay can handle things like NFS better and other features that regular overlay won't. So we'll use Fuse Overlay less, but we'll continue to use Fuse Overlay. And Fuse Overlay we also do for some experiments and new ways of handling different features. So I think we go to the next slide.
Yeah, I can take this one. This is not a big feature per se. It's just enabling extended chat with for NFS, but it's in the way we are planning to use it that I think it's interesting. Like Dan was saying that Fuse Overlay FS will be used for some experimental feature, and this is one of those. Like NFS, it's not user namespace aware. So when we run rootless container, the NFS storage will refuse syscalls like shown because it doesn't know that the user is allowed to change the file to the shown request it has raised. So when you run a local file system, the local file system is aware that the root in the user namespace has control over some additional IDs. But when it's a remote file system like NFS, it doesn't know about the user namespace setup. So it just refuses to chown to files to anything else that is different than the user that raised the request. So we are planning on using extended attributes actually to store the UID, GND, and the mode for each file, so that FuseFS translates back and forth between what it offers, what it shows to the container, and what it stores on the NFS storage. So that if you look at the NFS storage, then every file will have the same owner and the same mode, but the real ownership will be stored in an extended attribute that will be read back by FuseFS, and that will be what will be visible to the container. So a chown will be converted to a set exat, and a stat on the file will use a get exat for that file. Yeah. So that will this will help us to use NFS storage for rootless containers.
Yeah. So I just want to give you an example where this comes up. So if I have an NFS home directory and I'm running, say, podman build, when podman build is pulling down, say, a Fedora image from the internet, it's going to be writing out all the UIDs, all the root UIDs are going to be written out, by default as my UID. But then all of a sudden, say there's an Apache file inside of the image, and from what happens underneath the covers is Podman basically pulls down the file, writes it out as my UID on disk, and then does a chown of that file to say it's UID 60. So it'll chown it to UID 60 inside of my user namespace. And that all works on a local Linux system because Linux understands user namespace and says, okay, Dan Walsh can write out files as his UID, and he can also write out files that are in this group of UIDs inside the user namespace. If he went to the NFS server's point of view, he's seeing that Dan Walsh is writing these files as his UID on the system, and all of a sudden he sees the Dan Walsh process chown a file to a different UID. And from the NFS server side, seeing that, it says, no, Dan Walsh is not allowed to chown files to different UIDs, so it blocks it and gives you, and that's why up to this point, Podman will not run if you have NFS home directories. So with this handling of xattrs will allow us to basically use a Fuse file system where we're not going to chown it from NFS's point of view. It'll only be chowned inside of the Fuse file system through the use of extended attributes to that. A couple of problems with this. Since this is just showing up in these kernels, newer kernels, this is a client and server operation that's required to get the support. So what we'll see originally is only I'm not sure at what point the NFS servers, if you're using an NFS server, say from NetApp or something like that, I'm not sure when they will get 5.9 support for extended attributes support. So going forward, we'll get to the point where NFS home directories will work, but it might take some time because you'll have to make sure the client and the server have support for it. Next slide. All right, Rodrigo, we should make you talk about this since you jumped the gun on our slide. So, Rodrigo, this is sort of the holy grail of user namespace, and I've been whining about user namespace for probably the last 8 years. And so the problem with user namespace was always that in a perfect world, I would run every single container on my system in different user namespace. So any container that needs more than one UIDs, I want them to be isolated from all other containers. And so with user namespace, I could theoretically just pick 65,000 UIDs for this container, 65,000 for this container, 65,000. And as long as those UIDs are unique, then all of the containers will be isolated from each other because they'd all be running as different UIDs. Your root in one container would not be root the same as root in another container, and they would never be root on the file system. And that's sort of the promise of user namespace. The problem with user namespace, though, was always that the file system never had support for it. So I could take a container image that had multiple UIDs on disk on the file system, and I could run those processes in the shifted file system or in different user namespace, but they were never mapped. The file system would never shift. So if I basically said root inside of this container is going to be 5,000, then if I had a file system that was owned by really UID 0, that would look like an undefined UID inside of my container. What I would want to do is take that file system and shift it. So basically allow me to mount that file system so that UID 0 on the disk would end up looking like UID 5000, and then the user namespace would shift back. And I talked about this for, way back when user namespace was first being introduced into Docker back in 2013, 2014. Well, a month ago, thank God, it finally got merged. There's finally a file system support for this. Now, what we've done in our container storage for our rootless containers to support user namespaces, we actually have what we call a choning file system. So we chone the file. It's not really a file system. We chone the UIDs to work like this with some features and overlay, so that we could support user namespace and shifting the file system at this point. But our method of doing is very slow, right? It takes a few seconds showing an image. So with this new system, they'll be much faster. So this is a huge feature for allowing us to enable user namespace, and I think eventually allow us to use, to get to the nirvana of running user namespace inside of something like Kubernetes, where you could run lots and lots of containers with different user namespaces and be able to share the same image within all the different user namespaces, but have them different mount points be shifted so that they work inside of the user namespace.
Cool. We are right at time right now, so I'm unfortunately we're gonna have to call it. But yes, thank you everyone for joining. And I think you can continue the chat either in the event chat or in the session chat. But I will. Yes, it's time for the next session. So thanks everyone for joining.
Thanks. Are you planning on using OpenApt too for other components in runc?
I hope so, yeah, because for now that was more like a, I just tried using it for cgroups because it's easier and you have the prefix readily available, like sysfs cgroup, and it worked pretty well. And yeah, that's a big and complex task because we use Go runtime, not just the syscalls, and we cannot replace like open with open82. We have to write a wrapper. So probably the way to solve it efficiently is to add something into Go runtime, the standard library itself, or creating a wrapper that is similar to os.open in Golang, just with the prefix maybe and flags. So yeah, that's somewhat more complicated than you're using a lower level language like C.
So yeah, this is another part where C is better, I guess.
Yeah.
In C, and I'm using OpenApt already for solving the mounts. That's a question from by says, any plans to add ID mapped mounts to runc? I think there is an open pull request for the runtime specs to add support for the mount attributes. That there is a new syscall also added as part of the ID mapped mounts. That it's currently not possible to map with runtime specs, even though the ID mapped mounts will, for the container image, will be handled outside of the runtime, OCI runtime. There will be Dagger level tools like Podman, Cryo, Docker to manage the storage as they do today, is using choning. Or does Docker support shiftfs, like the out of it's supported by Ubuntu kernels? I don't know if Docker is using that. But anyway, for the image storage, that will be handled outside of the OCI runtime.
Yes. So what runc or crun does is it gets the file system already created for them, and they just run the container. The storage is out of scope for RCI runtime.
Yeah, so hello. I just want to add that for the storage use case, we have to wait until we have overlay FS support for ID mapping mounts. So the current solution only supports S4 and other file system, but yeah, we will have for overlay FS to be able to use that in containerd, CRI-O, and other solutions. And from runc, I think it still makes sense because we could share volumes between pods that are using different mappings. So that will be a use case for runc, and I think runc is the right place to implement that.